I'm Dr. T and welcome to my dining room table. So today I would like to talk about Lewis symbols. So this is a way of drawing an atom and representing its valence electrons. So remember, the outermost shell of your electrons is known as the valence shell, and this is what's going to be interacting with the rest of the world. By drawing Lewis symbols, we're setting the stage for future interactions with these atoms by looking at just their valence electrons. So I'm going to go through a few different elements, and we're going to see a couple of the quirks they can do. So let's start out with the simplest element there is, hydrogen. So hydrogen has in its valence shell one electron, because that's all it has. Hydrogen only has one electron when it's neutral hydrogen. Now, over here in this section, this is known as the s block, because these are dominated by the s orbitals in their valence shell. Now, hydrogen only has an s orbital total. It's very simple because it's a very small atom. It only has one electron when it's in its atomic form. So I'm going to draw an invisible circle around my hydrogen. The one side of the circle represents that s orbital. And then I'm going to put an electron in it by putting a dot. Now, I can put this dot literally anywhere on this hydrogen I want. It doesn't matter where I put it. And there, I have the Lewis symbol for hydrogen. Now, if I wanted to do helium, helium has two electrons, but it still only has one orbital. So I will draw an invisible circle around the helium, and I will put two electrons in it. Now, these electrons will pair up in that orbital, so I put them as a pair. Okay, let's move down a little bit on the periodic table. And let's go for, say, lithium. So in the case of lithium, now all of a sudden we are lower down on the periodic table. This first row only had s orbitals, or s orbital, singular, because it only had one shell. Now, for the second row, its second shell contains more orbitals. It contains an s orbital and three p orbitals. So instead of drawing a one-sided circle, we're going to draw a square. So I'm going to draw an invisible square around the lithium, and then into one of those orbitals, I'm going to put a dot. Which side of the square doesn't actually represent any of the particular orbitals. The trick with the orbitals is that they're only really orbitals in the sense that we've talked about them when the atom is completely by itself, nearly in a vacuum. Once it starts interacting with other atoms, the orbitals will rearrange and reconfigure. So the s, p's, d's are as kind of a starting spot, and those will morph into different things once it actually interacts with something that's not it. Okay, so I have the lithium. Let's try a few more electrons, though. Let's go up to carbon. So carbon now has a total of 6 electrons, but it only has 4 valence electrons. 1, 2, skip the middle, 3, 4. And that's usually how we count these things. Okay, so I'm drawing my invisible box around it, and I'm going to start putting them in one on a side. 1, 2, 3, 4. Yay, I'm done. I typically go counterclockwise, but once again, the sides don't actually have inherent meaning as to one orbital or another, so you can go in any order you'd like. There, I have the Lewis symbol for carbon. Let's kick this up a notch with more electrons. So let's go for nitrogen. Like carbon, nitrogen's got itself a box. So an invisible box. And now I'm going to start putting in my electrons. But how many do I have? 1, 2, skip the middle, 3, 4, 5 electrons. So 1, 2, 3, 4, and 5. After I've filled each of my orbitals, I start pairing them up. Okay, I can do the same for oxygen. Invisible box around the oxygen. And pretty soon you just don't worry about the invisible box. It's all in your head. So 1, 2, 3, 4, 5, 6. Because 1, 2, skip the middle, 3, 4, 5, 6. And so on and so forth. Okay, so yeah, this is the basics. But let's look at 2 more elements because they can get a little bit quirky. And those 2 elements are going to be our good friend phosphorus. And we'll do sulfur after that. But the reason I want to talk about phosphorus is down here. Now the D block, this area down in here, actually starts with the d orbitals above the d block. There are d orbitals that exist in this gap. Electrons typically don't go there. That's why there's a gap there. But they are there and they're in the valence shell. That means that aluminum, silicon, phosphorus, sulfur, chlorine, and argon all have d orbitals in their valence shell, but they typically don't use them. So I can typically draw phosphorus similar to the way I would draw nitrogen. I would draw a square around it because it's not utilizing the d orbitals typically. So I draw my invisible square, I put my dots in. Kind of got that first one a little bit off center, but okay. And there, I have my Lewis symbol for phosphorus. However, once phosphorus starts binding to other atoms, sometimes it will actually bring that d orbital into play. So the phosphorus can have a slightly different Lewis symbol. Typically, we don't write this out to start with, but once we start communicating phosphorus with other atoms, then sometimes we have to bring out this Lewis symbol. I'm not going to draw a box. I'm going to draw a pentagon. And thus, I fill it in as 5 unpaired electrons because one of them is in a d orbital. Now, I can do the same thing for sulfur. For sulfur, if I look over here, sulfur is next to phosphorus. 1, 2, skip the middle, 3, 4, 5, 6. So if it doesn't use d orbitals, it's going to look just like oxygen. And often it does. So I draw an invisible box around the sulfur, and I start filling in the sides. And notice how sulfur looks just like oxygen and phosphorus looks just like nitrogen. This is where we get our periodicity. The groups have similar chemical properties because their valence shells end up behaving very similarly. Notice the 5 electrons, 1 group, 2 unpaired for both nitrogen and phosphorus, and the 6 electrons, 2 grouped, 2 unpaired for oxygen and sulfur. Now, like phosphorus, sulfur can bring in d orbitals if it wishes to do so, and you will start seeing that in some compounds like sulfuric acid. So in that case, I'm going to draw my sulfur, and instead of putting a box, I'm going to put a hexagon. So, and therefore I'll have dot, 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 dot. Those are not intended to be paired. Typically speaking, unless you know otherwise, you always go with the square. This gives you the Lewis structure that these are most likely going to be, or the Lewis symbol that they're most likely going to be in. However, do be aware that they will occasionally transition into and use these d orbitals. I would actually like to draw one more, and that would be a nice noble gas. Let's go for neon. And in neon, if I look at the periodic table, I notice that he's actually high enough. He has no d orbitals, so he can't do anything but a box, but he can do a box. And I'm going to be 1, 2, skip the middle, 3, 4, 5, 6, 7, 8. Jumping the gun on that spec. 1, 2, 3, 4, 5, 6, 7, 8. Neon has all of its orbitals filled in its valence shell. That's why neon typically does not actually engage with other materials. It's a noble gas. It doesn't want to react. So with that said, these are Lewis symbols. They're actually fairly straightforward. What we'll do later on is start actually interconnecting Lewis symbols to start showing the relationship of atoms within molecules, and that's known as the Lewis structure. That takes a little bit more practice, but the first phase, at least in the way that I prefer to do Lewis structures, involves writing the Lewis symbols, and thus good practice to get started with until we jump into Lewis structures. With that said, have a wonderful day.